hosted by the Center for Global Security Research within the Lawrence Livermore National Lab. My name is Asmaret Asketom, and I'm the Associate Deputy Director of the Center. Today's speaker is Masao Dahlgren. Masao is a fellow with the Missile Defense Project at the Center for Strategic and International Studies in Washington, D.C., where he writes on missile defense, space, and emerging technologies. Prior to CSIS, he held positions at the U.S. Department of Justice's International Office, along with the Hudson Institute. Masao's lecture is based on a recent report he published with CSIS called Getting on Track, Space and Airborne Sensors for Hypersonic Missile Defense. His paper underscores the need for a new and advanced sensor architecture to detect, identify, and track different types of missiles, which are becoming increasingly difficult to detect. In terms of today's format, Masao will take about 45 minutes to an hour to provide his lecture. Then we'll head right into the Q&A session with the audience. Feel free to start raising your hands electronically and writing questions into the chat during the lecture. That'll ensure a smooth transition to the Q&A portion. With that said, Masao, it's my pleasure to welcome you to the lecture series. Thank you for joining us, and over to you.
Thanks, Asmaret, and I'm really grateful to you all for having me. I've read CGSR's reports for a very long time, and the great perk of my job at CSIS is I get to talk to the smartest people, I get to be the dumbest one in the room, and I get to learn something. And so I'm hoping today I'll be learning as much as everybody here, even though I can't see you in my screen right now. So looking forward to the Q&A. Just some brief context on CSIS and the Missile Defense Project for those unfamiliar. We're a 501c3 think tank in Washington, D.C., and my project team covers missile defense, but it's not just limited to missile defense, a wide variety of emerging technologies issues. Among the recent reports we've published, we're on space sensors and space-based missile tracking architectures, the missile war in Ukraine, and the use of missiles in Ukraine, and CUAS, countering small UAVs, unmanned aerial systems in general. Just a little piece about the pipeline right now for those interested. In the coming year, we're going to be releasing some research on the U.S. munition supply, a budget analysis of U.S. munitions. I have a lot of detailed slides, and forgive me for blowing through them, but just in the Q&A section, just a teaser for some topics to discuss. A program on directed energy, and I'm excited about this because I want to talk to some folks at Livermore at some point, especially anybody who's on the DPAL team. I'd be excited to hear. And then finally, I'll be authoring a paper on open source foundation models in the coming year. So these are some things we have in the pipeline. This is the kind of work we do. It's informed research for both the public and for the policymaker at the Missile Defense Project. But I want to get on track here, and I want to get on and talk a little bit about the report and the thought process here. And by the way, if there's any questions that come up partway through the presentation, I'd also be delighted to take them at various points. So, please feel free to inject a couple of them, through the presentation. The impetus for this report really was the growing DoD interest in producing a proliferated satellite architecture for tracking hypersonic weapons. Back in 2022, I authored a report along with my director, Tom Carrico, talking about the coming hypersonic threat and what we would need to do to get there. And, interceptors are one thing, but the number one concern moving forward, the number one blocker on progress was really sensors. Sensors capable of tracking hypersonic weapons, and they're predicting their trajectories in detail. Sensors that can detect the dim targets and construct a three-dimensional track. Sensors that are resilient to complex attacks in space or against airborne assets. And now, of course, there's a vision for that. The Department of Defense has multiple elements which are working on pieces of the problem. The MDA is prototyping a space-based sensor. It's entered orbit, HBTSS, to track hypersonic weapons. The Space Force and the Space Development Agency, its component piece, are going to develop a LEO architecture. And Space Systems Command, who I was speaking with just 2 weeks ago, is going to put about 27 to 30, 35 satellites in medium Earth orbit to track hypersonic weapons with an infrared sensor. This renewed priority is reflected in the budget. This is from the FIDEP from fiscal 24. If you look at the investment in MEO and LEO satellites in the coming years, it is beginning to really scale up. And the traditional approaches of sensing and tracking missiles from geosynchronous orbit is increasingly de-emphasized in future budgets. So I want to get to the top lines here. The report does a couple things. First off, it does an analysis. It unpacks the trade-offs involved with designing these architectures. We wanted to make sure the report was a cheat sheet for the otherwise uninformed policymaker on what trades are exactly being made in these architectures and how they affect schedule, how they affect cost, how they affect survivability. And out of that analysis, we found that perhaps the current approach from SDA, and what we're hearing from SDA, is that it maybe over prioritizes high inclination orbits, orbits that go over higher latitudes. The second top line point here is that we need to maintain a multi-orbit approach to sensing and tracking hypersonic weapons. There have been some efforts and some murmurs that we should focus most of our efforts in low Earth orbit. We contend that that would be a mistake. And the recent news about potential nuclear threats in LEO, potential space debris threats in LEO, potential cyber threats underscores that you can't just achieve resilience through proliferation. You have to achieve resilience through a complex set of approaches from more than one orbit. And then finally, there's an issue of fire control. Fire control is a difficult mission to distinguish from the other sensing missions here, but narrowly, it's about tracking hypersonic weapons with enough detail to actually guide an interceptor. The Space Development Agency is trying to develop a constellation that will do missile tracking and track the missile trajectories as they come through the atmosphere. But will that be enough to do missile defense fire control? And those requirements for how accurate that sensor will be is linked to the interceptor development. They cannot be disentangled. And we think that it will be very important for the SDA to not drop or abdicate that mission set moving forward, even though there are temptations to do so. So a couple things. The report unpacks some of these trade-offs in the architecture. We unpack system-level trade-offs in terms of the orbits that are selected, the inclinations that you choose, the number of satellites in an architecture, and we also unpacked sensor-level trade-offs. Narrowly, what kind of trades you might make in the focal plane arrays, the optics, the field of view of the sensor, and we try to explain this, again, at the highest level terms to the policymaker. We use two tools to do this. We use SDK. I write some custom code, and we also use a piece of software called SmartSet from Lockheed Martin that does missile defense laydown and horizon analysis. So on the right, you actually see one of the outputs from our simulation runs in SDK. This was some genetic optimization we were doing to size a particular constellation. And so onto the fun stuff. How do we unpack some of these trade-offs, at least at the sensor level? We created a synthetic environment. We made a scene on the left that imported some infrared background information from NASA VIIRS, and we developed some models, and I don't have the skin. I don't have the skins that actually have the temperatures, but 3D models that kind of represent a hypersonic threat. And so we can put these into visualizations and use the EOIR suite to actually show what that tracking challenge looks like, what the relative motion challenges look like from LEO, how dim these targets on and whatnot. And in this case, I've enhanced the image to make that target visible, and the bore site is completely aligned with the hypersonic weapon. But in the real world, right, we want to show the policymaker how hard it can be to track these weapons. On the left is a raw sensor readout from our simulated scenario, the raw look at the scene. And the hypersonic weapon is diluted by the pixels around it such that you can't really see it. And then on the right, you actually see the extracted target. I used some custom code to ingest about 20 frames of scene data and assess the optical flow, the actual motion vector of each pixel, which is represented in the false colors in the middle. And then you're able to kind of pull the target signature out of that. Because again, hypersonic weapons are point source. They are smaller than the pixel, the actual resolution of the sensor that's looking down on the Earth. And so it is difficult to distinguish how hot or dim that pixel might be. Now, the reason I'm talking about this at all is because that impacts the field of view you might select for the satellites. If you have a narrower field of view and you're holding the resolution of the sensor equal, you might have higher sensitivity to detect these targets. But that comes at a cost. The narrower you make your field of view, in fact, if you go from 120 degrees to 110 per satellite, you roughly triple the amount of satellites you might need in a LEO architecture. So sensor level trades are tied in with architectural trades. And the architectural trade in the forthcoming Department of Defense piece, the Department of Defense architecture, is really the matter of LEO, MEO, and GEO. How do we balance capabilities across those orbits? And how do we design a capability that gets on coverage? And in the past, various DoD entities have used different standards and different language for articulating their goals. Now, what do I mean by this? The Space Development Agency is going to buy 135 plus satellites for an architecture in low Earth orbit. This architecture will have infrared sensors on these satellites that will look down at the Earth and track hypersonic weapons notionally. And in order to track them, you will need at least 2 satellites to have access on the point of Earth where the hypersonic weapon is. You need the weapon viewable by at least 2 satellites to construct a 3-dimensional track. So you need stereo tracking. And moreover, you'll need a satellite overhead at all times, right? So you need it to be continuous coverage, not just coverage every now and then. It's a different mission from remote sensing, where you might have a couple revisits every day as opposed to 24/7 tracking. And so in their plans, SDA and SSE and other parts of the Space Force have talked about achieving regional coverage by a certain point or global coverage by another point. But oftentimes these come with caveats, right? For a long time, SDA liked to talk about regional coverage. By regional, they meant satellites would be over a region of Earth at some point, not that there would be continuous coverage over a given region. Or you would sometimes hear talk about global coverage, would be global coverage, but only by one satellite persistently. And so really what we're talking about and what we need to get to is persistent coverage, stereo coverage, and global coverage, right? It has to be persistent. There has to be 1 overhead, 2 overhead at all times. It needs to be stereo. There has to be 2, and it needs to be global. And so, one finding that we made was that the current architectures leverage highly inclined orbits. Orbits that mostly traverse closer to the poles as opposed to closer to the equator. And a constellation like this, for instance, of just one orbital plane, technically provides global coverage. A satellite will cover the globe at some point, through its orbit. And you might say it provides regional coverage, right? It covers a region of Earth at some point in time. But I don't think this meets the standard for persistence. I don't think this meets the standard for stereo coverage, right? And so, the current SDA architecture puts together a number of these highly inclined orbits, right, into a constellation. 135 satellites in 9 planes, for example. This is a notional constellation we make, provides global persistent coverage, right? Where red is the densest coverage of 8+ satellites, and yellow is the lightest coverage of 2 satellites overhead at any given time. But the problem we find with these highly inclined constellations is that they do not deploy gracefully. You don't get persistent coverage of the Indo-PACOM region that you care about until nearly every single orbital plane is deployed. This is the same constellation with 2 orbital planes or 2 of these rings removed. And you get these giant holes in coverage that traverse around the Earth in the Indo-PACOM region. That doesn't meet the need for getting regional coverage earlier. And it doesn't meet Congress's call to achieve Indo-Pacific coverage before getting to global coverage. And so the finding we had here really was that, there are different ways to ramp capability, even if the final capabilities are the same. It's easy to talk about the coverage you're going to achieve once all 135 satellites are deployed. But more attention needs to be paid to how we get there. And if getting there means having no coverage or very little persistent coverage for quite some time and then ramping up to complete and global coverage, architecture B, versus another architecture like architecture A that could phase coverage in more smoothly, we would prefer to pay an extra cost maybe to get that smoother phasing. We can't afford to create constellations where if they were canceled partway through, if the threat changed partway through, if something were to happen partway through its deployment, that you wouldn't get that much usefulness for the warfighter. Because as it stands, right, when we look at the SDA's plans, these are visualizations of their forthcoming architecture in Tranche 0 and Tranche 1. They're mostly focused on these highly inclined orbits. And it was only in a recent RFI that they paid a nod to deploying at lower inclinations, right? So how do we phase in coverage more smoothly? One approach is to potentially phase in 2 steps. So you might deploy a smaller constellation that's focused on the Indo-PACOM region, and then expand it with a couple satellites to cover the poles and get global coverage. So, for example, this constellation here is a much smaller number than 135. I think it was something like 60-something satellites, right? With only that much, you could get coverage, persistent coverage of that strip near China, near the South China Sea, near Japan, near Korea, near our allies that we really, really care about. And then in a second constellation we add later, that's roughly 30 satellites, 30 to 40 satellites, you could get to that global coverage. Another approach is really to leverage multiple orbits. Low Earth orbit is useful for the cost of producing and putting them in orbit. But it might be viable, it might be useful to put satellites in other orbits that have better coverage characteristics for those really stressing areas of the Earth. For example, low Earth orbit constellations are very good at covering the poles. The most efficient way to minimize the number of satellites is to have a really highly inclined constellation, and I think that's why it's being done. But of course, it provides the thinnest coverage near the equator. So in this kind of visualization, you can see there's really thin coverage near the equator with this kind of constellation. But with the addition of a medium Earth orbit layer, for example, you might be able to cover up some of the weaknesses of LEO without having to create a really dense low Earth orbit constellation just for Indo-PACOM. that MEO layer is about 8 satellites, right? Which is added on to the roughly 60 or so in the blue. And so you can get to global coverage that way without having to construct like a second step at these low inclinations that takes a lot of satellites. Now, the third way we think you might get to smoother capability phasing is, of course, to leverage alternative domains altogether, right? Space has its advantages. There's not much cost to upkeep. You can keep them in orbit for some time, though with LEO, you're going to have to be constantly replenishing those satellites. But even from the air, you might be able to get some longer range sensing than you would with a ground-based asset against hypersonic weapons. The technology for these kinds of systems exists. It would be off the shelf. And for some limited applications, like in the defense of Guam, you might be able to develop a system that provides interim coverage as these constellations come online. And so, looking ahead, there's a couple policy temptations that I think we have to watch for. The first is, of course, to consolidate into single orbits or single domains. The recent intelligence release on Russian nuclear activities is one of them. And when I presented about this report back in December, I was on a panel with some senior DoD folks, SDA, Deputy Assistant Secretary Hill, some others, and we raised the question, if there was a nuclear detonation in LEO, you could pump that environment and take out many satellites at once. Should we be worried about that? What are we doing to deter that? And I think the answer we got back in December was, well, Russia would never do such a thing. It wouldn't be in their interest to do so. But as the United States increasingly relies on proliferated constellations of many satellites, on military versions of Starlink to do communications, to do missile tracking, to do, left of launch targeting, to do all these other functions, there will be more and more incentive, even if it's extremely costly, for adversaries to use nuclear weapons in low Earth orbit, or to use other means like generating debris in low Earth orbit to try and attack these proliferated constellations. These proliferated architectures are great, right? They invert the traditional economics of counter space, right? It might become cheaper in the very near future to put satellites up into LEO than it is to shoot them down with most means. But these threats are evolving, and we suggest that there needs to be more attention to that. Kind of relatedly, we suggest that a multi-orbit architecture is useful for these exact reasons, right? The DoD's efforts and SSC's efforts to produce a medium Earth orbit constellation, in addition to the coverage benefits that I talked about earlier, also impose some attack synchronization challenges for an adversary. If it takes a couple hours to hit something in GEO, or an hour to hit something in MEO, and it takes 30 minutes to hit something in LEO, then for you to hit all three of those things at the same time, you will have to launch your attack at different times. And so you will get some advanced warning of it happening. It introduces complexity into Russian and Chinese war planners' heads that can make them less inclined to maybe use counter space capabilities against an architecture. There might be temptations in the future to cut things down and to just go to PLEO for everything, proliferated LEO for everything. But we think that would be a mistake. We need to lock them out at every single orbit. And the question now is how to find the cost-effective means to do that, right? And we think in the end it might save some costs, especially given the coverage benefits of deploying in medium Earth orbit, for example. I guess the second temptation, though, is this optimization issue. I think somebody from industry once told me that when they were looking at the Space Development Agency's proposed architecture for low Earth orbit sensors, that it looked like a telecom constellation. It was completely built for coverage efficiency over everything else, on minimizing the number of satellites you would need for global continuous coverage. But less attention, again, has been paid to how we get to that deployment, how we sort of scale things up before we get to that global coverage with 135 satellites. Because again, the SDA plans to get there, in the early 2030s, late 2020s. Now, is that sufficient to meet the threat that is potentially planning to achieve military modernization by 2027? How can we make sure that we get coverage of the areas we care about the most, especially around Taiwan? And shouldn't we design architectures that cover those areas first before covering the poles? I mean, this is a debatable point, but it is worth considering alternatives that are available. I guess one note I'll make, though, is, again, we're not engineers. We're not here to prescribe a specific architecture that you should choose. We have a lot of mixes of different LEO, MEO, and GEO systems that we've proposed. Oh, did I get logged down?
No, you're still in.
Oh, goodness, WebEx showed me a little bit of a blip, but I'm glad that I didn't get logged off. So you could, but there's a lot of LEO, MEO, and GEO systems that could be used, and we're not here to prescribe an architecture or to tell engineers how to do their job, but just to illustrate that there are alternatives, alternative directions to examine, because I guess in the initial formulation and the initial force design, this wasn't considered as much. And then finally, when we're looking at temptations, there will be a temptation to abdicate the fire control mission. And I touched on that a little bit in the beginning, but there are three distinct missions that we're looking at, and that the Space Force is looking at when buying these constellations. There's the traditional missile warning mission that's done by SBIRS and DSB that will warn of nuclear attack. It will feed into ITWA, the nuclear attack determination system. It does tip and cue for the MDA through a network called C2BMC. And it does all of those functions, including some limited missile tracking. And then there's missile tracking, right? This mission that could track and generate trajectory predictions for hypersonic weapons in particular. And that's being pursued by the Space Development Agency in their new low Earth orbit satellites, and by SSC, the Space Systems Command, with their medium Earth orbit satellites. It's unclear whether you can do it from GEO without having like a huge aperture to look at the Earth. But, and that's great. And then the third mission, of course, is fire control, right? A version of missile tracking that especially has lower latency. Significantly reduced latency is really, really important for predicting the potential intercept point, where you could launch an interceptor and it would fly out to that area and plausibly hit the target. And for every loss in precision, in terms of the space or in terms of time, you will have to design in more and more requirements into the interceptor. You'll have to make the interceptor bigger. You might have to make it heavier. You might have to make it more agile. You might need a more sophisticated onboard seeker to compensate for a reduction in sensor accuracy. And so this really matters, right? The Missile Defense Agency is developing an interceptor through the Glide Phase Interceptor Program. It's planned to get online in the 2030s, early 2030s. The Congress wants IOC by 2029. Contracts have been awarded, and there's two design teams working on it. But how do we make sure that we can make their job easier by making the sensors better? That's what we're thinking about with fire control. Now, the Missile Defense Agency was previously tasked with developing a sensor that could do that. And if you go back to the fields of view that we were examining, we actually know the field of view for some of the SDA sensors. They are going to basically cover almost the maximal breadth of the Earth they can cover from that altitude. And so, they're a wide field of view sensor, a WFOV sensor, fixed, pointing at the Earth, and they're going to have to detect hypersonic weapons. And so the footprint of each pixel on the Earth is going to be relatively large. And that poses a sensitivity problem, but it also poses an accuracy problem in terms of localizing where a hypersonic weapon is, right? And so the Missile Defense Agency sensors are apparently a narrower field of view. They have a skinnier field of view, and they will be slewed by like a gimbal so that they can search a wider area and be kind of cued to look at a potential threatening object and image it in greater detail. Now, that's one approach that's being looked at. And the question is whether that kind of technology will be transitioned into the forthcoming architecture. But there are other pathways maybe to getting to fire control. Another one would just be to increase the resolution of the sensors. There's an effort internal to SDA to do that, to look at 6K, 8K, 12K sensors instead of the 4K that is mature. And apparently there's issues with yield in order to get the industrial base to produce those sensors at large scale and cheaply, for these proliferated architectures. Another approach, right, is to pull in this HBTSS gimbal solution into the architecture. And that's being done partly in the next 2 tranches of SDA's purchases, but it's unclear really where that will go. Tranche 2, which is coming online in 2027, is supposed to have 6 fire control sensors. And 6 by 2027 is not very much, and certainly not enough to do stereo tracking. And so how do we get from here to there? That's a question that we need to answer, and that's something that we call policymakers to be on the ball about. And I could go into more detail. That wraps the major section of the presentation, but I also want to bring up one final thing that I think would be of interest to the folks, especially at Livermore, right? And that's that hypersonic weapons are unique. In our report in 2022, we really established that these systems are not invincible. And in fact, hypersonic weapons introduce new characteristics, new types of vulnerabilities that can be exploited, right? The same things that make them so threatening to our current missile defenses, our ballistic missile-focused missile defenses, make them vulnerable to other types of modalities, right? And on the kinetic side, right, there's the fact that they lose energy in certain turns, that they have a budget for maneuver, that they might be vulnerable to particle impacts and other issues like that. But there's also vulnerabilities on the sensor side. And this is something I want to learn more about and something we might have a discussion around, right? Hypersonic systems emit unique signatures. The DoD has focused in this 5 billion plus architecture mostly at infrared, detecting hypersonic weapons with infrared sensors, trying to fuse the views of multiple sensors with a fusion algorithm into a 3-dimensional track, potentially tracking them from MEO and LEO at the same time, trying to figure out all the math to do that, right? But they also emit a lot of interesting signatures not in infrared. At those hypersonic speeds, air is ripped apart into ions and the surface of the hypersonic weapon is heated and releases certain gas species and other chemical products that might be detected, right? And this is a major area of forthcoming research and something maybe some of the audience is more acquainted on than I am. But it's not just thermal, right? There are other signatures to chase after. And so the question is, how might we get at that? And this is probably a subject for a follow-on report. How might we get at other phenomenologies? How do we make the case for other phenomenologies for tracking these systems? Because there's a lot, and I name a couple, right? You might have hyperspectral approaches to doing it, multicolor, infrared to do it, passive RF, these systems emit radio waves that could be picked up. But there's also more exotic approaches, right? in terms of, RF with incidental reflections, for example. And I knew some folks working in the weather community that are maturing that technology quite quickly. And so, in the forthcoming discussion, I'd love to hear and just talk about maybe those alternative phenomenologies when it comes to missile tracking, missile sensing. So that about concludes my remarks. I'd be happy to go on into more detail on any of these slides or any of these pieces. Uh, I try to be very conscious of time, but it looks like I've come under. Thanks so much.